Okay, so I'm gonna give a talk that initially you will not believe that is related with divisibility, but you will see if you are a little bit patient that it is. The talk is going to be a bit peculiar in the sense that we have a very long motivation, almost maybe even longer than what is going to be the body of the talk, because I want to present you a theme that you may have heard about laterally. You may have heard some news about it, and that involves the possible coherent dynamics that is undergone by molecular complexes that are involved in some processes of interest in biology, in a sense that I will make more clear. So then what I really want to explain very as clear as I can is the reason why, despite a large body of methods have been deployed, it's been very difficult to reach a conclusion that is as uncontroversial as it can be when heavy experiments are involved. And then to motivate how actually deploying very abstract formalism can in fact be helpful to in fact move from a lot of qualitative discussions into something more quantitative, that a little bit in the spirit of Bell inequalities, we do an experiment. We are not aiming to identify specifically what type of hidden variables theory may actually be able to reproduce the observation, but it's more the idea of saying this class of theories can definitely not do the job. Okay. Right, so let me put you in the right framework. So we are dealing about open quantum systems, right, where the system of interest in our case is going to be made of a complex with highly absorbing molecules that can interact dipolarly, and they are embedded in a protein scaffold that you can already think of as a path of phonons. Right. In a cartoon-like, these are typically embedded in membrane proteins. Here is the small connection to biology, in the sense that we are going to be interested in processes where, following irradiation, something is going to happen that for, let's say, a femtosecond to picosecond time scale will then trigger photosynthesis, fission. So we are in the very, very primary steps of a complicated reaction that underpins, as I said before, phenomenology that can be relevant even in natural systems. But for us, what is important to keep in mind is that we are dealing with ultra-fast processes that have a very, very high yield. So these are examples of quantum systems that are performing in very noisy conditions, and nevertheless, they are able to actually perform very, very efficiently. If you want to already think about what sort of physics is involved, trying to build up ab initio, a Hamiltonian that will be describing the process, then you can think of having some type of dynamics that will involve exchange in between the components of this aggregate. But what is important to keep in mind is that we have a very large body of measurements in the traditional applied physics sense that are done even without a theory underpinning it, as opposed to quantum optics that we can theoretically predict some nice Rabi oscillations are going to happen. Here we are doing experiments where really we go backwards to build up what the theory is. The important is that these are experiments where coherence can be created in some steps, and then there is going to be a time of free evolution and coherence will be probed once more. So I think what I showed you before is the typical scheme for performing, which is called multidimensional spectroscopy. But if we bring it down to basics, this is a glorification of a Ramsey setup. So imagine the simplest case where we actually have a complex that is made up of only two pigments that are dipole. So this dipolar interaction, if you diagonalize it, right, we may have eigenstates that are localized. And imagine some experiments tell us that the lifetime of having superposition between the ground state and the first excitonic state is 50 femtoseconds, right? We now do an experiment that will probe a different type of coherence. We create initially a superposition of the two excitonic states, let them evolve, and then probe them again. Well, then we know that depending on the phase relation that has been built up during the time evolution, if they will be along in the universe evolving unitarily, then the type of signal that we will obtain is just Rabi oscillation. And if the system is noisy, if something else happens in between the two Ramsey pulses, then this oscillation will be smoothed out. Okay, so what was surprising in these experiments is that this lifetime I told you between the ground and the excited state, very short-lived. It seems that now we observe lifetime for these excitonic superpositions that last even one order of magnitude larger. So you may have heard the word in long time coherence. This refers precisely to the difference in time scales between superpositions ground excited versus the lifetime of superpositions that concern the new excitonic eigenstates. Okay? So what is surprising for the moment with quotation mark is having femtoseconds in here, and then coherent oscillations that can be observed experimentally, extending, let's say, into the picosecond time scale. Why is that relevant? Because in the picosecond time scale, relevant things can happen. So for instance, that's the typical excitation time in going from a reaction center, from an antenna to a reaction center in certain photosynthetic complex. Questions come. Is it relevant? It's simply a byproduct that we are really probing experimentally, timescales where maybe is obvious in a sense that some remnants of quantum coherence remain.
I just as a question, the parameter you talked about is this omega 1,2 on the previous slide, which is the surprising one. The rate of the oscillation, the omega.
No, the lifetime you observe here, right? So let's say if you would superimpose here, what would be the lifetime of a coherent superposition, 0E1, right? You will encounter that actually the lifetime would have lasted much shorter
It's the length of that. picture.
Exactly, is if you want the duration of the oscillation period or the lifetime of the superpositions. Mm? So the question is, why is it the case that the environmental fluctuations kill these ground excited superpositions so fast, while I'm able to maintain in time coherent oscillations of the excitonic states? So that's what was puzzling.
So, but the process that's happening there is just decaying again to zero, let's say.
Sorry?
So that the oscillations are damping because the state is decaying to zero. Or
Well, let's say that eventually these excitonic superpositions could decay, right? In the sense that you may end up with a mixed state or whatever. In reality, what happens is that the next process after transfer will kick on, right? And then this coherence that can be maintained can then be relevant for whatever comes afterwards. Okay? As I'll show you in a moment. So the question is, does this matter? Is it relevant that these type of superpositions could be long-lived in these timescales, or is a byproduct of being probing very short timescales? So somehow putting together different observations, what comes out is that these aggregates seems to be operating a little bit sitting in the fence, right? Like exploiting certain level of coherence, but not too much. And at the same time, exploiting some dissipative processes that appear when they couple to the surroundings. Hmm? Now, how do we make this blah blah more quantitative? Hmm? Well, take into account that if you would like to start now doing calculations with the Hamiltonian I showed you, the first thing you need is some input. You need to know what are the energies of the different chromophores that make the aggregate. And you would also like to have some values for what sort of couplings to put. Hmm? Well, in this case, the way you do that is starting with whatever information you may extract from crystallography, for instance, or really seeing distances, orientations from the structure itself, determine some possible couplings. And from this initial guess, then you have to fit all the different figures that the spectroscopists have measured. Linear absorption, different forms of dichroism, and then a bit like in cosmological models, right? You may start to make the input Hamiltonian more and more and more accurate. Hmm? If you start to look at the type of parameters that come out from these fittings, then you realize that here we are in a situation where thinking about doing an analysis from the point of view of open quantum systems is a little bit dubious, in the sense that where to put the border system environment and have the possibility of doing some perturbation theory is compromised, because all the standard approximations that you would like to do, Milanjana was invoking weak coupling this morning, they are not obeyed. Everything, let's say, electronic excitations couple between them and to the surroundings with comparable intensities. So we would like, especially in the light of having conclusions are less model dependent as possible, we would like to do numerically exact simulations, taking into account that if we look at the spectrum of the fluctuations, if we look figures of merit like the spectral density, then we realize that they are heavily structured. So the type of things you would really not like to see if you are trying to derive some form of tractable master equation. So this is an example of a measured spectral density where you see that in addition of having a complicated initial part, mainly responsible for the dephasing, we also have very messy contributions in the high energy part. Nevertheless, if we push state-of-the-art numerical methods, we can do an exact treatment of dimeric structures, including, let's say, a spectral density with 50-something peaks. So we did an analysis of one complex that appeared in cauliflower, probably relevant for biology, but possibly very relevant for biology is the special pair that appears in the reaction center. The reaction center is the responsible of producing charge separation, and biologists think that this is very likely to be the process that has been optimized by nature, taking into account that the geometry that is observed for the arrangement in reaction centers in fact conserved across species. So it's likely that there is some reason for that. So we deploy the best methods that we have, which essentially try to map out typical star configurations into something that is amenable for doing the MRG. And I just show you what would be the first type of experimental data that you would like to reproduce, and that's an absorption spectrum. And here we have a numerically exact calculation depending on how do I treat the spectral density, whether I perform a brute force embedding or whether I'm sequentially from M20, 40, 55, include all the different peaks that have been observed. Then you see that I get things that are really very different depending on whether I do include or I don't include the high energy contributions, right? In such a way that to perfectly match the experimentally measured absorption spectrum, I do need to fully consider the real spectral density. Now, remember that all the parameters that concern the system dynamics, right, are obtained by a fitting. This fitting strongly depends on the spectral density. So therefore, should you make the determination of your system parameters, in particular the couplings, with a certain form of the spectral density, you will get Hamiltonian A. If you do it with another one, Hamiltonian B, another one, Hamiltonian C. What happens then? That the interpretation you do of the experiments that are able to check for coherent behavior vary. Okay, so if you look, if we take us state of the art, at least from part of the community, on what is the answer, on whether we can say that experimentally long-lived excitonic coherence have been observed, it's unambiguous, and I invite you to have a look. Very much they, at least this group of authors, advocate this type of picture that we did initially really with reduced descriptions, in the sense that, okay, the dipolar coupling may lead to the formation of the localized excitons, and then really they thermally relax, right? In the sense that there will be an optimal level of the dephasing noise where actually the efficiency of the transport is maximized. But we think that this is not really the case. if we take into account the fact that you will obtain different excitonic dynamics depending on how you did the fitting, right? This points to the fact that unless we do a numerically exact analysis of the different forms of spectroscopy, then we are in a conundrum. In other words, the reason not to be able, I would say at this very moment, of arguing what is exactly the physical origin of the observed oscillatory behavior relies in the fact that in this case, linking unambiguously the spectral response and the underlying dynamics is not one-to-one. Yeah. So this is the, let's say, qualitatively the idea I want to put forward. Okay? If I do fittings now of the spectral response, the multidimensional, so where really I can follow what would be excitonic tracts, right? Then, even that I have an ambiguity on the level of the coupling, right? It may be that actually signals that one thing that maybe they correspond to oscillations between the ground state and one phonon actually do correspond to excitonic superpositions that have the same energy gap. So I would argue that the problem is open until we are able really to compute exactly the multidimensional spectral response and being able to include truly the spectrum of the fluctuations in terms of having an exact spectral density as an input, then you being able to conclude whether or not we do have long-lived excitonic coherence remains an issue. So there are oscillations, plenty of them. Now associate them directly to say, okay, this is unambiguously a signature of excitonic coherence is what remains open. So I hope I've been clear in conveying what is written here in the box. So the issue for the disputing here is this impossibility to link A if and if only if B. Why is important? And this, I think, comes to the question that Ludovico was saying. Well, if you think about these complexes in a sort of thermodynamical picture, you can imagine that, think of photosynthetic complexes in particular, right? You can think of them as a system that is performing some work, able to deliver some power, some work per unit time, operating in between some sort of incoherent radiation from the sun, so heat reservoir, and then they dump excess energy into a cold reservoir, polonic, right? Imagine two different models in here. Inside the system, I consider one case where the only degree of freedom that is involved is the dipolar coupling between molecules. And a second model where actually I do have, in addition to this coherent interaction, a coupling in between each chromophore and some selected vibrations. So that coherence built up at two levels. One at the level of excitons. I think the formation of the localized excitons is incontrovertible, right? And in addition, there could be coherent exciton-phonon interaction, so yielding, if you want, to the formation of truly vibronic states. Well, the efficiency of those machines is different. So in fact, if I look at what would be the typical current voltage curves, and therefore identify what would be the power delivered depending of whether true vibronic coherence buildup is such that I have an additive component to the total current related with the power the machine can deliver that is only present in the case where the excitonic relaxation doesn't proceed thermally from the highest exciton to the lowest one. So the fact that excitons hybridize with the surrounding phonons leads to an increased efficiency. So this could be an argument to think that maybe the role of coherence is not a byproduct of the time scale of the dynamics, but may actually have a possible functional role in the sense of being able to assist the PGT. Okay, so this is the background that I hope you understand what the motivation is to think whether we can actually provide any further insight if we forget about the microscopics, right? That you see that there are many problems to really A, to build an ab initio Hamiltonian, and B, even if you would have it, to actually be able to compute accurately the spectral response. So, are there other tools that maybe would shed light into this issue? Well, we argue that resource theories could actually provide additional information. So the idea is I forget about Hamiltonians and now I want to be able to perform different types of experiments that can tell me something. For instance, can assist me in to discriminate whether in a given process, I will simply have the formation of some delocalized excitons thermally relaxing versus another situation where actually the transfer is much more complicated. So the analysis will not tell me exactly what is going on, but they will tell me, for instance, something very useful, like saying, forget about it. Here there is something much more involved that thermal relaxation of the excitons. Okay. Right. So I think many of you are familiar with the spirit of resource theories. So the idea is to identify classes of operations, right, that we consider to be free. And therefore, this will set a value into states that are outside that free set and that can become resources to perform some task that the free set cannot perform. So the most elaborate of the resource theories is the resource theory of entanglement. You have as free elements performing local operations and exchange of classical communication and have product states, then entanglement becomes a resource in this situation. So what happens if we consider another type of restriction? What we're going to consider in our case is a resource theory of abnormality. So then the three processes for us are going to be thermal operations, right? We can also bring in baths at a fixed T, and we will be able to perform partial traces. So the idea then is seeing whether we can already obtain some type of properties that our process will have to obey if it can be modeled in terms of these thermal operations. So as a reminder, we define as those operations that conserve energy globally, okay? So one immediate consequence is that, well, there are times translational covariant and the evolution of all the coherent sectors is going to be decoupled, right? So populations and coherences will evolve independently. So even two states, rho I and rho F, when is it possible that such a transformation can be implemented by a thermal operation? Well, here we are lucky because it's possible to have an operational criteria that will tell us whether or not I can transform thermally by means of a thermal operation, the initial into the final states. And it effectively amounts to implementing a form of partial ordering that will dictate whether indeed such a transformation is feasible. Let's say you can think of an algorithm that will be able to construct this very much generalizes what we know for majorization. So we will build a form of ordering that allows to have thermal majorization curves in such a way that a process will be allowed or not. One state will be thermal majorized by the other, depending on whether the thermal majorization curves are like in the left, the process is allowed, or if there is some crosses, we know that the thermal connection is not possible. This is equivalent to actually analyzing whether we can find an stochastic matrix that is linking the input and the output state. And can be more or less laborious to do, right? But the point is that it can actually be implemented, even in a process that a priori may look sort of messy. So we chose, actually following an initial idea of Nicole Junger and David Lima, we focus on one of the reactions that I think, as far as I know, is the fastest in biology, that is the photoisomerization of retina. So one of the ultra-fast processes that happen in the retina prior to vision. So this is a change in between two stable configurations of the molecule, whose nature from the microscopic point of view is still under debate. So the experiments point towards having, show you this one, having in fact a true conical reaction forming, so a hybridization with phonon modes. But how does retinal manage to be in an initial configuration, be photoexcited, and then something happens in such a way that I end up with another stable configuration? The microscopics of it is not known. So very much as in the cases we were discussing before, so we know that there will be some form of barrier to be crossed. We know that this chromophore is embedded again in a protein scaffold. So what has to happen for, in a very short time scale, end up with a very high yield in the another stable configuration is not known exactly. So what we are trying to do now is saying, can we model actually this process in terms of a concatenation of thermal operations? Nicole and David actually propose a minimal model photoisomerization where actually think about a dividing here. This would be one stable configuration or another. You only need 4 states: ground and first excited, ground and first excited in the second configuration. And in fact, we actually showed that you can't forget about the state W prime. So the thing is that not all final states are achievable via thermal operation. Therefore, resource theories will not tell you what is going on in between, but they will be able to characterize how much population you can actually observe in the second stable form, right? If the underpinning model is thermal. So the figure of melt.
What are the free states in this?
Okay. So in each configuration, I just consider the ground state and the first excited state. Yeah. So if you irradiate the system, that would be the first operation. You will be able to move some population from 0 to W. Then something magic happens, right? And then you will encounter that some population have moved into here, right? So ideally, what you would like is that essentially all the population was transferred to the ground state of the second configuration. Okay, so the point is that actually to determine what is the yield, it can be shown that you don't need to include these 3 states. So if you want, from a computational point of view, here you would be dealing with determining what is the optimal G matrix for a population in between the levels of a Q system. It's important to keep in mind that under thermal operations, you can't forget about the differences. They will not assist the process, right? So everything reduces now to analyzing how you can transform population 1, 2, 3, population 1, 2, 3, with the restriction that the action has to be thermal action.
A non-free state would be one where the 4th level is postulated, or what?
No. The point, if you want, you can put it, right? The point is that from the point of view of the yield, right, what final population ends up in here is actually not relevant. You get the same optimal yield, just modeling with a 3 level and with 4th level, plus an order or something. Okay, so the thing is that actually you can even analytically obtain what is the optimal yield. So you can characterize how much population should be observed experimentally in the isomerization process, should the underpinning dynamics is capable with a thermal operation. Okay? So that would be an observable quantity, right? That should you be able to measure, right? It will tell you, if I do an experiment and observe an isomerization yield exceeding this bound, then I know that the description I need to do is such that it cannot be just a thermal operation. So it will be a case where you know that indeed this idea of having possibly a conical intersection in fact makes sense. Don't simply create a delocalized state in the molecule that when they'll simply relax to another lower energy localized state of the molecule. In between, something has to happen with the phonon modes. So where does divisibility come into this picture? The formulation before is the typical situation in resource theories where you have an input-output description, right? I prepare, there is a thermal option, then I have an output. But we would like also to be able to make predictions concerning a continuous dynamics. So I want to exclude, I want to extend the definition of thermal operation to, I call it here thermal process, but maybe we should call it a thermal dynamics. And the definition we propose is that I will introduce absence of memory in the process. So I will call a thermal process to be, in addition, Markovian. It is such that obeys the divisibility condition that has been introduced in detail by Darius. So I don't need to go into details. Maybe you see it pictorially in this manner. So the calculation I showed you before will correspond to this case. I can determine what is the optimal yield in an input-output formalism, with the only restriction that the process can be modeled in terms of a thermal operation.
You say what this means for the L of T's before? Right,
Sorry?
you have the L of T's in your Markovian evolution.
Yeah.
General have the L of taus. I mean, do they also have restrictions to be thermal, the L of taus, or is that completely arbitrary?
No, this would be completely arbitrary, right? The only thing is that I adopt as my definition of Markovianity, right? The fact that the divisibility condition for the dynamical map would be obeyed, and therefore I can identify a possibly time-dependent generator that is of form.
Yes, but you also impose thermal, right?
Wait, yeah.
And thermal, I don't see where the thermal condition is in the L of tau.
So this, just only to remind the divisibility, the definition. And now it comes, how do I define what would be a thermal? Yeah. So the way we define it is then imposing that at every step, right, I do have local thermality. This is a very strong condition, right? But it's the only definition that we were able to find in such a way that I do preserve then a separate evolution for populations and coherences. So my definition of thermal Markovian processes imply local thermality.
And can you then characterize the L of taus which are possible? If you do these two conditions together, this must give some
the functional form.
Yeah, the L of taus, which are then possible if you combine Markovian and thermal.
Right. Take into account that here the explicit characterization of the form of the generator is not relevant. In fact, that's what I don't want to do. But what we can do is continue the yield. Local thermality is obeyed. And it's different from the optimal one, as one can imagine, right? So we can then determine also analytically what is the form of the now thermal Markovian optimal isomerization yield, and then compare it with what would be the optimal when you just thermally relax, and the asterisk one would be the corresponding to the most general thermal operation, which could be non-Markovian or non-thermal. Yeah. Okay, so here comes a bit the connection I mentioned at the very beginning with hidden variables. Let's say that should I perform an experiment and determine the isomerization yield, then I can put a bar saying, okay, if I think of what is going on in the underlying dynamics, I know the most general will be a emissivity map, then possibly the isomerization yield will be equal to 1. Then it can be a thermal operation, a Markovian thermal operation of just a thermal equilibration. Should I get a yield like the one in the figure? Then you know that modulo the definitions given, I have some memory involved in the isomerization process. Or if I go above, then some certified thermality. So resource theories, I mean, I would argue that it's a very different way to address the type of discussion I posed you at the very beginning, right? So we saw how difficult it is to move ab initio. So this type of analysis then would allow you to at least benchmark classes, saying, forget it, this is not happening just forming the localized excitons and going down the ladder. We are exploring now really whether indeed the bounds we are getting, that's another problem, maybe they are too loose. So we're trying to see, for instance, and also considering experimental data, whether we can build Hamiltonians that are able to saturate the theoretical bounds. And also, and this is something that I would be very open to hear some ideas, is to see whether we can relax the definition we have done where thermality is imposed at every time step. So whether maybe it's the case that from input to output, the process is thermal, right? But I could be able to have different values of the yield without involving explicitly memory, but breaking the condition of thermality at intermediate times. Take into account that in that case, the evolution of populations and crossings in between the different coherent sectors will happen. And this is open how to proceed in that case. So then I conclude just thanking the people that have been involved in the second part. In the first one, I compress in 10 minutes the work of many years. Many years where we really have to develop completely new numerical routines to be able to include these ugly spectral densities.